Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're solving examples demonstrating buckling applications in columns. The next example is a design example. The problem statement reads, a column with pin-pin boundary conditions is designed to support an axial load P equals 150 kips. We're to design the column by selecting a wide flange steel section from among the W10 sections given in the table below. Here's the table. This table is a partial list of sections, and the table has been adapted from Mechanics of Materials by Timothy Philpott, Wiley, 3rd edition. In our design, we need to allow a factor of safety of 1.5 against buckling or yielding, and the yield stress of the steel is 36 ksi. We should also use E of 29,000 ksi for steel and a column length of 12 feet. Based on those criteria, we're to choose the most economical or lightest section that satisfies. So let's go ahead and work the problem, starting by summarizing the given information. We are given that the load P on the column is 150 kips. The column has a length of 12 feet and it's pinned. I'll make a little sketch. Here's my column, pinned at both ends. Have an axial force P of 150 kips, and the column itself is 12 feet long, and it's pinned at both ends. Okay. We also are given that the yield stress, sigma y, equals 30 ksi, elastic modulus, 29,000 ksi, which is a typical value for steel, and we want a factor of safety of 1.5 for buckling or yielding. So it should be at least factor of safety of 1.5 for both. We are to find the best or lightest W10 section that satisfies the criteria. Okay? So we have to evaluate both buckling and yielding criteria. We'll start with buckling. Buckling criteria is that the actual P, the design load P, has to be less than or equal to P crit divided by the factor of safety. I can rearrange this to solve for a minimum P crit that the column has to supply, which is equal to P times the factor of safety, which is 150 kips times the 1.5 factor, and that's 225 kips. Okay, I'm going to equate that to the equation for P crit, pi squared EI over L squared. I know everything but I here. I is a function of the cross section, and that's what I need to determine. So I can rework that equation to solve for a minimum required I for this section, which is P crit L squared over pi squared E. I'll go ahead and substitute the numbers. 225 kips times the length of the column, 12 feet or 144 inches squared, divided by pi squared, divided by the elastic modulus, 29,000 ksi, and that gives me a value of 16.3 inches to the fourth. That's the minimum required moment of inertia for the column. Next, look at my yielding criteria. The yielding criteria is the actual stress, sigma, that results in the column from the axial force. Sigma has to be less than or equal to sigma y, the yield stress, divided by the factor of safety. Sigma y is 36 ksi, divided by the factor of safety of 1.5. This is 24 ksi. So sigma has to be less than or equal to 24 ksi. I'm going to relate that to the actual load P in the column. P is equal to sigma times A. I'll rework this equation to solve for a minimum required cross-sectional area A, which is P divided by the sigma allowable in the column, which is 150 kips divided by 24 ksi, and that equals 6.25 inches squared. So that's my minimum required cross-sectional area. To summarize, I need a section that has an I a moment of inertia greater than or equal to 16.3 inches to the fourth, and area greater than or equal to 6.25 inches squared. And let's look at the table. Start with area. This is the column for area right here. We see immediately this W10 by 12 does not work because the area is less than 6.25, so I can cross this one off. Otherwise, the other three all satisfy the area criteria. Next, the moment of inertia criteria. The moment of inertia has to be at least 16.3 in both directions. The weak axis buckling is going to govern. That's this column right here. And we see that, oops, that's 116 there, but we see that each of these also satisfies the moment of inertia I-min criteria because they're all greater than 16.3. So basically, any of these three sections will work, a W10 by 30, 45, and 60. We want to choose the lightest one, and if you recall the designation for a wide flange section, the first number is the depth. They're all about 10 inches deep. The second number is the weight, and it's given in pounds per linear foot. But the weight is directly proportional to the size, and the lightest section is the one that is going to be the most economical. So we would choose W10 by 30, 30 pounds per square foot, or per linear foot. And it has the smallest area and the smallest eye that satisfies the criteria. So to summarize, the answer is simply choose a W10 by 30 for design. And that completes this problem.